think I'm going to start. We might be a minute early, but we seem to have a quorum here, so let's get going. I have this tendency to begin my presentations with a bit of a warning. In other areas of science, when we're interested in physical phenomena or mathematical descriptions, usually you're encouraged to look at the science, make models, execute the scientific method, and so forth. That's not the case here. In this area, if you look at experimentation, if you look at models, if you try to execute the scientific method, you're likely to have your career destroyed. And if there's anybody here that's not clear on this, let me take the opportunity to make you completely clear on this. You become interested in the field or you work in the field at the peril of your career. People say that it shouldn't be that way, but it is that way.
Is there any reason to this?
There are reasons. There's lots of reasons, which I'll explain shortly.
Okay.
Why a new course? There's lots of reasons. You need understanding to develop a new technology. There are claims. There are new technologies coming online, if you like, and we'd like to have understanding in order to evaluate them. Last year, I didn't get any phone calls of people asking if was anybody trained up that they could work in the area, but the year before I had like 4 phone calls. And sadly, there's fewer and fewer people in the field. Not so many people are trained up to work. Also, to be clear, MIT would never approve at this time a course in this field for credit. This is not a course for credit. It's an independent activities period, and people can get up and present on whatever they please. So that's what this course is. The area is controversial. There are many issues not settled. There's a lack of acceptance by the scientific community. At MIT, this happens in some areas where we do teach courses. No reason not to have a course. So the objectives of this course, the field is very broad. There's a lot of effects. There's charged particle emission, neutron emission, there's tritium production, there's transmutation. The focus is going to be on excess energy production, Fleischmann-Pons and Fleischmann-Pons derivative experiments. And there's a lot of reasons for that. One reason is that in spite of this being a 5-day mini course, within 5 days we're not really going to be able to do what we need to do even on this topic. And in such a short time to try to dilute things to focus on the other topics would be asking too much in my point of view. I'm going to be interested in why it's important. A very big issue here is the separation between known science and new science. The idea is that there's a very large body of experimental data, and turns out we're going to find that we can make a huge amount of progress by considering the experimental data and experiments themselves in terms of well understood science. At some point, we're going to run out of steam with well understood science. We're going to have to consider new approaches. We're interested in experimental issues. We're interested in theoretical issues. There's on the order of 1,000 theoretical papers out there. We could have a month-long course reviewing all of the theoretical approaches. I'm going to shortcut it, and I'm going to focus on one theoretical approach, and that's going to be one that my colleagues and I have focused on, and so forth. It turns out there's implications for condensed matter physics, nuclear physics, and perhaps other areas of physics as well. Because of the nature of the course, I'm going to be trying to section things into small bite-sized sections. So there's going to be an introduction and a summary at the end of each section. It's the only way we're going to survive. The place to start is Wikipedia, of course. I mentioned to one of my students last year, or a couple of years ago, I was going to be giving a short course on my area of research, IAP. She goes, well, what are you working on? I said, well, I work on cold fusion. So she said, well, that sounds interesting. So she said, she went off immediately and fired up Wikipedia to see what Wikipedia says. And after looking at Wikipedia, she came back and she said, well, I looked at Wikipedia, so I know about cold fusion now, and I'm not going to be attending your course. So that's okay, I understand. So, cold fusion. In Wikipedia changes from year to year. And in earlier years, Wikipedia actually had a halfway decent account. One of our colleagues in the field would update the Wikipedia page. However, that anchored some of the skeptics who had him banned, and now Wikipedia is a little bit more in the straight and narrow. So it's a type of relatively low temperature nuclear reaction reported to have occurred, but which others haven't been able to reproduce, and it's disputed. Of course, Wikipedia keeps up with the times, and Wikipedia is advanced. So last year and this year, we have a slightly different story. Now it's a hypothetical type of nuclear reaction. It's not a real nuclear reaction, hypothetical type. It's proposed to explain reports of anomalously high energy gain in cold fusion experiments. Has been rejected mainstream because couldn't be replicated, and there's no accepted theoretical model. So that has to set the stage here for our discussions. There's this discussion of the excess heat as being distinct from cold fusion. Cold fusion includes all kinds of anomalies, but we're interested in excess heat. So what does Wikipedia say about excess heat? Oh, basically it's a small effect, 10 to 20% effect. Now, being a 10 to 20% effect, we have it from Wikipedia, probably it's a mistake. I mean, who can measure something at 10% anyway? It's just a little tiny effect. So forth and so forth. There are other tidbits that are interesting, but by now you should be getting the idea. In this version of it, we find that Nate Lewis discovered that the excess heat, Fleischmann-Pons' original paper, was not measured, but only estimated from experiments that had no excess heat. So I give you Wikipedia. There are other folks working in the area. Shanahan works at the Department of Energy laboratory and did an analysis of problems with cold fusion experiments for the Department of Energy. And quoting from his paper, we've got the following conclusions. Many positive results. High signal to noise ratios normally computed for a very high signal to noise. And they're in noise. I think this may be a typo. I think it's noise to signal ratios. According to Shanahan, there's noise and systematic errors. Seeing cold fusion calorimetry is currently at or near the limits of accuracy and precision. So we can see that cold fusion has the problem it's a tiny signal. Calorimetry is only so good, and so there's difficulties measuring that. We'll see lots of examples, I guess. Mitchell, probably the effects that you see are within the limits of calorimetry, probably. Takeaway message. The first takeaway message is, can't trust Wikipedia. Who can we trust? Everyone already knows about cold fusion. Everybody knows it can't be reproduced. The field's discredited. As mentioned, working in the area destroys your career. Even being interested in the problem is problematic. And from my point of view, this is a motivation to air it out, think about it, discuss it. Look at the experimental results, think about the implications, look at the models. And this is why it needs to be better understood. Okay, for these takeaway messages, me pause and catch my breath and entertain questions or comments. Are there questions and comments?
Seems like you're done here.
Yeah. All right, well, thank you for your attention.
There is no improvement from last year. So last year there was a certain, let's say, negative feeling about this field, but results of the last year didn't change.
Well, it depends on who you're around. For example, if you wander through any of the halls at this institution and babble about positive results in cold fusion, you'll find a different reception.
I have known some credible researchers in Japan who are in this field, and they seem to be having the same problem in terms of career. For example, Dr. Arata or Takahashi, and I'm wondering what can change, what can trigger the change of the perception from the
Nothing. It's hopeless.
What can trigger this?
I don't think anything can change it. For example, you would have imagined that you could change things by doing good experiments, getting reproducible experiments, doing better measurements, but it has no effect whatsoever. I don't think anything can change it.
I just want to let everyone know that I'm recording this. I plan on putting it online, so if you don't want to be recorded, you want me to take you out or edit you out, just let me know after class, and I'll edit you and take your voice.
We need to have a free discussion here, and there are laws in Massachusetts about.
Exactly. So if you want, I'll edit it out and won't go online. Period.
Good. Have yourself or any colleagues, or any of the folks in the community that contributed and tried to influence the Wikipedia entries? For instance, it is a shared resource. If anyone's done that, it's been undone, or has anyone tried to turn the tide of at least?
Yeah, one of my colleagues actually contributed halfway decent discussion. It was all taken out and he was banned. I tried to explain to them that what they were saying was basically propaganda.
Editors at large there.
And they explained to me, they said, well, unfortunately, this is how things work. So,
I just want to make a comment. I think it was Max Planck who said that if you have new science, it won't be accepted by the present generation. It will be the new generation. So, if you're talking about whether this will be accepted at some point, it may be.
I don't actually expect it to be accepted in my lifetime. All right, the experiment. Let's talk about the experiment. So Martin Fleischmann, Stanley Pons, in a different time, in a happier time. Here's the cell. Let me talk briefly about the experiment itself as to why it was done. There's been questions since 1989 as to why Fleischmann-Pons did the experiment. And Fleischmann himself has given many explanations. I asked him a year roughly into this, I said, why did you do the experiment? And his response was, back in the 1950s, it was known in the electrochemistry community among senior electrochemists that there was a problem with the accuracy of the calorimetry. If people would do calorimetry with palladium hydride, they could get 1 part in 1,000 accuracy easily. But when experiments were done with palladium deuteride, that typically is a % kind of error under conditions where there shouldn't have been any error whatsoever, at least a part to 1,000. This wasn't understood, and Martin saw it in his own research in the late 60s, and at some point in his career he wanted to return to it. The idea is that maybe he jiggled around with it, he could make it from a 1% effect to a 2% effect, and maybe 2% to 5%, and 5% to the 10 to 20% that Wikipedia discusses. So that was the motivation for the research initially. Here's the cell. I'm not sure what to say. If you haven't seen the cell before, you might look at it. It looks like a complicated drawing. I guess the thing to do first is to look for the cathode. Here's the cathode, palladium rod. And then look for the anode. So here's the anode, and it's spiral platinum wire around. So there's electrolyte, heavy water with lithium deuteroxide. For discussion for another day, there's a reference electrode here. And that will become interesting tomorrow or the next day. Here's an observation reported and published by Fleischmann-Pons in 1990. So here's the temperature change. It's a maximum temperature change, well, between here and here is, it's like about 15 degrees C, and the peak is like 27 degrees C. So is that at the limit of calorimetry? Can we measure that?
Not quite.
No, maybe not. Okay, so the amount of excess power production in this experiment was prodigious. The ratio of output power to input power is a factor of 20 at this point. So I'm not exactly sure what Wikipedia is referring to as the 10 to 20% effect. It was a much larger effect, certainly when initially proposed, and as we'll see later on, also large effects subsequently. The total amount of energy produced is about 630 kilojoules in roughly 60 hours in this experiment. So if I divide 0.63 megajoules by 60 hours, I get just under 3 watts. The total amount of energy is a very large amount of energy. So how do we picture how large the energy is? Well, one way to picture is to take the cathode, which had a volume of 0.157 cubic centimeters. If we were to take that cathode and replace it with TNT and detonate it, we would make 1.2 kilojoules. Fleischmann-Pons saw 630 kilojoules. The amount of energy under discussion is a very large multiple of what you would expect from chemical processes. I mean, it's been suggested many times that all that's happening is there's some strain energy in the palladium that's being released. The strain energy would be a tiny number compared to the total amount of energy that's produced. The effect is not chemical, as we'll discuss further. In the cell, we have electrolyte, D2O. We have palladium cathode, palladium reference electrode, platinum anode, and glass, and the various connectors that you see. If you made that much energy chemically, there should be easily observable products. Fleischmann's conjecture was that the energy produced is of nuclear origin, and furthermore, his conjecture is perhaps some kind of deuteron-deuteron fusion reaction of some new kind. Fleischmann, if you hit this in the early days, he's a chemist, and when you have chemistry, you have a barrier that prevents reactions. So his view of nuclear reactions in those days is sort of like a chemical picture. But maybe if you can get the deuterons close, there's a barrier, you overcome it. Chemical level barrier is what he was imagining. And then something would happen to give you some energy out. However, as has been pointed out many times, there's no commensurate nuclear radiation. And you can see that here's Fleischmann-Pons around the cell, and I don't see lead bricks here. This was discussed as the dead graduate student problem, that if it had been fusion and you'd gotten commensurate amount of neutrons out, you should have had health problems. Okay, takeaway message. In the Fleischmann-Pons experiment, a very large amount of energy is observed. Unlike what's described in Wikipedia, it's not a 10 to 20% effect. It's a much bigger effect. There are not commensurate chemical reaction products. There's no commensurate nuclear radiation. There were issues with reproducibility in 1989 and 1990. For example, long afterwards, So my friends discussed with Martin, I said, well, what's the reproducibility that you had in 1989? Well, something in the neighborhood of 1 to 5 to 1 out of 10 of his own experiments worked. So in his own laboratory, the reproducibility at that time was not very good. And then we have the conjecture that there's new physics involved. Comments?
And I assume there was no helium or even a fission product, a fusion product. Did they try to measure helium?
In conventional DD fusion, helium-4 is a minor product, as we'll discuss, and it's when it's produced, it comes with a 24 MeV gamma ray, and I can pretty much give you a money-back guarantee based on the photograph that we saw that there weren't watts of 24 MeV gammas coming out at that time. That there would be health issues with that. Other comments or questions? Okay, so now I've caught my breath, so I can go on. Implications. There are implications for this result, which is why it attracted so much attention. I was looking over my view graphs last night, and I see that I've managed to have view graphs here that focus on an equally contentious issue. One thing that's not contentious is that CO2 in the atmosphere has been increasing. The CO2 ages and ages ago, back around 1700, is somewhere under 280 parts per million. And recently, one of the Mauna Loa measurements gained notoriety for getting us over 400. Why is that important? Well, it may be important, may not be important. Some people think that CO2 as a greenhouse gas, along with methane, nitrous oxide, and tropospheric ozone, is related to temperature increase. So the thought being is that there are models now that are predicting the temperature is going to be going up. I guess given the weather here lately, that wouldn't be such a bad thing. It's been very cold lately, but I actually think it is temperature raised climate change, if it's due to mankind's impact, it is very definitely a bad thing. Okay, so if Fleischmann-Pons experiment is true, if the excess energy is real, then it points to all kinds of things. It suggests there's a possibility of clean nuclear energy, which would be an alternative to oil, coal, natural gas. There's no greenhouse gases. We'll be talking soon about helium-4 as being produced from it. And helium-4 in large quantities make you sound like Mickey Mouse, but it rises to the top of the atmosphere and boils away. It's not a greenhouse gas. For the heavy water experiments, there's lots of deuterium available. There's estimates that per gallon of seawater, the amount of deuterium in, which is on the general order of 1 part in 6,300, provide enough energy to be the equivalent of something like 1,000 gallons of gasoline in terms of its energy content. Good energy to weight ratio, which would be important for robotics, space travel operations. Clean water is extremely important. Some significant fraction of the people on the planet right now do not have access to clean water. And if we could boil water, we could evaporate it and distill it, get clean water that way, and do it easily, that would have a huge impact on the lives of a large number of people. The DOE, the original DOE ERAP report was a very negative report, but I want to draw attention. A simple way to harness this energy in the excess heat in the Fleischmann-Pons experiment would be an extremely important discovery. Also, from John Huizenga, who wrote John Huizenga was a co-chair of the DOE ERAP board, and he wrote an unbiased account of cold fusion and his experience with ERAP. in his book Cold Fusion Fiasco of the Century. According to Huizenga, if true, extraordinary accomplishment. So DOE ERAD, John Huizenga, you have it from the most skeptical of the skeptics that energy production of the Fleischmann-Pons experiment is a big deal. And if it's real, it's important. Takeaway message. The big implication of Fleischmann-Pons is that there's the possibility of new physics which could allow for clean nuclear energy production. There are a very long list of subsidiary implications having to do with the impact on physics as we understand it today. The world's facing issues with energy, other problems stemming originally from overpopulation. Overpopulation is at the root of many of these problems, and that's what really needs to address, and cold fusion will never address that. However, energy from a Fleischmann-Pons-based technology could provide a fundamental solution to some of these big problems, at least for breathing time enough, perhaps, for us to get our population under control. And this is why it's important. Let me pause. We're at the takeaway message slide. Thoughts, questions, comments?
I read that in this process, not so much neutron and gamma ray come out as it should.
There is no evidence for gamma ray emission in connection with the palladium deuteride experiments. I think by the time we get to Friday, I'll talk some about gamma ray emission in connection with the nickel hydrogen experiments. And there actually is one observation which is really interesting, which we'll talk about, actually from one palladium deuteride experiment where gamma rays were observed. Small amount.
Now, the deuterium, that's produced by electrolysis of seawater, isn't that correct?
You mean the deuterium used in the experiment?
No, I mean, I'm saying if this becomes real and there's a need for deuterium, where would it come from? You mentioned seawater.
Right. I think separation of deuterium from hydrogen from seawater or from fresh water is an obvious source for deuterium.
That's an electrolysis process. Is that right? Like, I'm just asking.
There are many ways to do it. There's usually multiple methods.
Okay.
Electrolysis usually gives you about 70%. So there are successive ways concurrent exchange. I reviewed that in the paper. If you give me your email, I'll send you the paper.
Okay, thank you.
Question. Okay, so caught my breath. Okay, given that this is significant, then the question is, how do we figure out whether it's true or not? So I'm going back to 1989. Fleischmann-Pons have just made their announcement. Here's this astonishing experiment. Clean nuclear energy from an electrochemical experiment in a test tube. Big magic with big implications. The question is should we believe it or should we not believe it? And that's what faced the scientific community in 1989. There was speculation. Dick Garwin, Dick Garwin is the fellow who bolted together the first hydrogen bomb experimentalist and became famous for it. He was head of research at IBM. He was head of the Jasons. He was one of the most powerful physicists on the planet and remains so even today at age 80 or so. Multi-dimensional resolution, I bet against its confirmation. And Dick Garwin today still bets against its confirmation. So this experiment that was done at CalTech, this may be the most important of the negative experiments. I was looking at this paper again last night. You give the course again and again, you see new things in it. Do you remember where the anode was placed in the Fleischmann-Pons experiment? The anode was spirally wrapped around. The question is, why was the anode spirally wrapped around? Well, among some of my friends who work on the Fleischmann-Pons experiment with lithium deuteroxide electrolyte as opposed to Mitchell's experiments, the idea is that you'd like to have the anode be all around the electrode, basically to provide a source of current from all directions. The idea is if you provide a source of current from one direction preferentially, that gives you places where the current can go, or the deuterium can go out in the other directions. So in this particular case, the platinum anode is here, and the palladium cathode is here. It's not wrapped around it. Anyway, CalTech did not see positive results. This was I don't know. Nate Lewis was the electrochemist, and Nate Lewis is a very famous electrochemist, and much more famous after 1989 than before, I think. The calorimetry was done. The heavy water experiments gave power balance to within 5%, which is close to the accuracy of the experiment. The experiment was monitored with nuclear diagnostics. Had there been fusion, neutrons would have been monitored, but there was no sign of neutron emission. The Harwell experiment is particularly important, and one of the reasons that the Harwell experiment is important is because Harwell was working with Martin Fleischmann in order to try to help provide a replication. So we see the experiment. Here's the palladium cathode. You see the platinum anode wrapped around. So this is a little bit closer, at least in spirit, to Fleischmann-Pons design and their experiment. And negative results were reported. No excess power, and especially damning because Fleischmann was a consultant on this experiment. So here's no excess power. So this is percent excess power. Here's 0, here's 10%, here's 20%. Here's result for heavy water, a little bit above 0, but it's within the error bars of the experiment.
They had 4 major bursts at Harwell. And the reason they managed to get the data to disappear is they divided by the 60,000 minutes. They used, instead of using a time-varying width for the denominator, they used a gradually increasing denominator.
The Harwell data was subsequently analyzed, and evidence for excess heat was found, but you're getting ahead of my story here. Bell Labs, at one point, was the jewel of the American Industrial Applied Physics Labs. Bell Labs was one of the most famous labs around. And with the stroke of a pen in Congress, various tax laws were changed, which made it more profitable to companies to do less research for a while. So Bell Labs was basically dismantled at the time, which in my view is a tragedy. Bell Labs did an experiment. Hundreds of experiments were done. CalTech was most important, MIT was important, Harwell was important, Bell Labs was important. And then there were 100 other laboratories. So these are standing in for the many negative results that were observed. So here's 0. Here's 20 millijoule per second, nearly 20 milliwatt. Above 0, the input power was 1,300 millijoule per second, 1.3 watts. So this is small, so this is within the error bars of the calorimetry. So this is a negative result. I mean, I think it's a negative result. I don't think there was any excess power there. The MIT did an experiment, and it's shown here. It was very well insulated, We have platinum anode, cathode. This has got to be the palladium cathode. Platinum RTD here. Alumina insulation here, calibration curve. And here's zero excess power. In fact, the total energy production in this data integrated over the lifetime it turns out to be exactly zero because it was calibrated based on assuming that there was no excess energy production. So the MIT result was very influential. There's a lot that could be said about it, and more will be said about it before this conference is over. I think even today, I think MIT takes pride in its. A lot of people at MIT take pride in the participation of MIT in this controversy and helping to resolve it to show that there was no excess power.
But my understanding is there's a controversy there. I don't want to get into it too deeply. Is it your opinion and that there was excess power and it was just?
I differ from Mitchell on this. I don't think there was any chance whatsoever that any excess power could have been made in that experiment, for reasons that we'll talk about shortly.
Okay. Another question is, going back to 89 and how science goes about trying to replicate other people's experiments. It seems like CalTech, Bell Labs, all these folks, they took a very crude path towards trying to replicate the experiment. For instance, the electrode wasn't wrapped. During the scientific method in the process, is there a normal method as to how close someone tries to replicate an experiment? It seems very crude. Why would they expect to replicate it if they didn't?
Actually, your comment's a fantastic comment. In fact, such discussions occurred in 1989. For example, the CalTech folks got up and they said, here's our experiment. We saw no results. And one of our colleagues, Bob Huggins from Stanford, popped up and he said, well, your loading's not high enough. And the response was, our loading is plenty high enough. There's no effect there. So according to the folks at CalTech, according to the folks at MIT, according to the folks at Harwell, they executed what, in their view, was a completely satisfactory confirmation experiment, and the results were negative, proving that there's no effect. I believe that if you talk to Nate Lewis today, you talk to Ron Parker today, if you talk to Mark Wrighton today, I think that you would find satisfaction that they would consider experiments were very well done. They clarified the experiment by doing that research and showed that in fact there was no heat whatsoever.
But it just seems like using the delta between the type of experiment that was done by Pons, Fleischmann and Pons and these other labs, you could make it fail if you wanted to.
I don't.
It's so great. So I'm just wondering, in the scientific process, how is that usually judged? Whether folks are close enough to or not?
As it turns out, I do not believe that all of the teams who set out to replicate Fleischmann-Pons did so in order to make it fail and set up their experiments on purpose to make it fail. I do not believe that. You might point out that in 1989, when, for example, the MIT experiment was done, there wasn't a lot of information about the Fleischmann-Pons experiment available. So that's a fact, and we'll discuss that shortly, but that does not in any way diminish the enthusiasm of the MIT experimentalists, the CalTech experimentalists, the Harwell experimentalists, Bell Lab experimentalists, IBM experimentalists, and many other experimentalists as being completely convinced that they tried a confirmation experiment and they showed that it didn't work.
Is there such a thing as a definitive negative experiment, or only positive experiments definitive? I mean, just in the philosophy of the scientific method.
Your questions are very good. I don't know that there are answers to your questions. Okay, on the order of 100 or more confirmation experiments run 1989, 1990, resulting in no excess heat. This is from Dieter Britz, who kept publications and reports from the labs that did them at the time. The takeaway message: Fleischmann-Pons experiment, as we've argued, is a big deal. If it's such a big deal, we need to make sure whether it's right or not. One way to be sure whether it's right or not is through experimentation, in particular confirmation experiments. Many experiments were done. Good scientists from good laboratories were involved. They were not able to reproduce excess heat in the Fleischmann-Pons experiment. And this was interpreted by many as positive evidence that the effect is not real.
And looking at those experiments and also reading some of the recent papers, and this is my view that the way how they prepared metals are quite different from how they do now.
Yes, we will talk about exactly that shortly. However, these issues were discussed in 1989, and the senior members of the scientific community decided officially that they weren't important.
And also, they, in his Huizenga's book, I had an impression that he had an agenda there to kind of.
If you read what Huizenga says, Huizenga came into the discussion completely impartial. He followed the data where the data led him. He thought about the theoretical implications and where that led him. He bent over backwards to be as unbiased as he possibly could, and he came up with a negative result, that there wasn't anything there. And he explains exactly how he went through it in his book.
He was mentioning about polywater incident, and he was comparing this Fleischmann-Pons.
Well, if you've come to the conclusion that the experiment's incorrect, then you have to figure out some reason why an experimentalist previously with such a good reputation as Fleischmann, namely Fleischmann, had won the Palladium medal from the Faraday Society, which is an enormous honor. So he had previously been well regarded within the electrochemical community. Among the electrochemists, measurement of enthalpy at the percent level at that time was an easy thing to do, and the signals were claimed to be much bigger than that. So I remember back in 1989 when this first broke, some of my colleagues said, Fleischmann's doing an experiment within his area of expertise. It's an enthalpy measurement in a calorimetric experiment. That's what he's good at. So either the result is correct, or else Martin Fleischmann's gone mad. And they spoke to him on the phone, and they decided from conversations they seem not to be mad. That's the way my colleagues have done it. But Huizenga came up with other ideas as to why Fleischmann-Pons might be reporting a positive result under conditions where it was clearly impossible, and where other people didn't see it. We'll talk more about this. Other comments or questions? Okay, what I want to do is I want to segue into the problem of DD fusion in the case of molecular D2. This was very important in 1989. This was taken as being a representative example to understand what was going on in palladium deuteride. So deuterons are composed of nuclei, which are positively charged and electrons on the outside. The positive charge of the nuclei pushes them apart. And pushes them apart so much that you need a lot of energy to overcome the Coulomb barrier to get them together. So, for example, the cross-section, you have a pitcher throwing at the plate of a batter trying to swing. The strike zone is an area, and the strike zone might be cross-section for a strike, and this is a little bit like what a cross-section is for DD fusion. So it's, I guess the joke is that back when nuclear physics started, you know, what's the appropriate size of a cross-section? He can't hit the broadside of a barn. So 10 to the minus 24 centimeters is a barn, which is the unit of area associated with a cross-section. So here we have a barn. Here's the DD fusion reaction. And here's a million electron volts relative energy. If you're down at 10 or 20 keV, you can begin to get a little bit of cross-section here. These numbers are pretty small down here. And if you're at room temperature, you've not got enough energy to get the two deuterons together because they push each other apart so effectively and efficiently. So to get around that, DD fusion currently is envisioned as being done in a magnetic fusion system at ITER. I downloaded this from the ITER website. This is a very large instrument. It's a multi-billion-dollar, multi-year effort. ITER expects certainly to reach scientific break-even, and I think they expect to exceed that by a significant amount in the coming years. If you like, one of the very big issues is that currently in science, to get fusion to work, this is the scale of device that you need to make in order to get heating enough and confinement good enough to get the deuterons together to be able to fuse.
Speaking of scale, how big is this whole unit?
I have an earlier picture that had the size of a man. Here's
there he is. Okay.
It's big.
Put some molecules together.
Yeah. Well, it's basically to get strong magnetic fields that can confine the plasma. So you heat the plasma, you get the collisions, you get the fusion to occur, and then you got to recover the heat and keep from degrading the system and so forth. But very sophisticated device. This is one of the pinnacles of modern applied science. So the statement that you can do what this machine does in a test tube without shielding and so forth, you can understand now the source of the issues, the scientific issues involved. Namely, if you can do it in a test tube and you don't need billions of dollars in many years in a large instrument, then that makes a big difference. And the judgment of the scientific community is that it's impossible to do it in a test tube. Let's consider tunneling. Tunneling is a quantum mechanical effect. Many of you have probably seen tunneling through a barrier. You send in a wave goes down, make it through the barrier with small probability. It's a quantum mechanical tunneling effect. In the molecule, D2 has a potential. If the two deuterons are sort of the right shape, there's overlap, there's hydrogen bonding, and you get a minimum at 0.74 angstroms. When the two deuterons get close together, the Coulomb repulsion pushes them apart. So this goes like 1 over r at close distances. And you can do a tunneling calculation, which in this case basically means you calculate the molecular wave function. So here's the peak of the wave function showing up at 0.74 angstroms. And in this region is where the Coulomb barrier is. And you have to get down a very tiny place to where the two nuclei touch one another to within the Fermi scale, close enough to be able to fuse. And if you see all these lines here, probably you can't read this, but this is 1, 10 to the minus 10, 10 to the minus 20, 10 to the minus 30, 10 to the minus 40. There are a lot of orders of magnitude the wave function goes down, and the associated probability goes like the square of this. So the probability in a molecule that two deuterons overlap is a very small number, and that means that fusion is very unlikely. There were calculations that were reported in 1989, 1990. This is by Kuhnen and Nauenberg. I'm Kunin, of course, being famous later on for being Undersecretary of Energy. So that's under Steve Chu recently. So here's D plus D fusion, and here's the number minus 63.5. The way to read this is that the fusion probability per molecule is 10 to the minus 63.5 per second. That's a very small number. P plus D is 10 to the minus 55. It's 9.5 orders of magnitude larger. So it would be much more probable. It's larger because the reduced mass is smaller. So let me think about the result briefly. So the fusion rate for the molecule looks something like this. And we can think of the fusion rate as being made up of different factors. There's a tunneling factor that says, you know, how good can you tunnel through the Coulomb barrier? There's a ratio between the nuclear volume and molecular volume. Basically, you're starting this big, you've got to squeeze down to being this big. So there's a volume factor on top of the tunneling factor. And then once you've started from big, you've tunneled through the Coulomb barrier, and you've gotten down to a small scale. And the question is, how long does it take for things to happen once the deuterons get close enough to touch? So that's a time constant, tau. We got tunneling factor, volume factors, and time constant. The volume factor is about 10 to the minus 15. The tunneling factor's about 3 times 10 to the minus 70. And the rate at which something happens once you get them together is 10 to the minus 21 seconds, roughly. So if you like, in this simple analog model, so the idea is that maybe in palladium deuteride, you have something that looks like a molecule, and to have fusion, you've got to overcome the volume factors, you've got to overcome the Coulomb barrier to tunnel in, and then you have this lifetime thing. So the understanding back in 1989 was based on the D2 molecule as an analog. The thought being is that the volume factor is not going to change very much for D2 in the palladium deuteride. Tunneling factor can change some by screening. Maybe instead of 10 to the minus 70th, maybe it's 10 to the minus 60th or something like that. And this time constant is determined by the local microscopic nuclear physics, so it's not going to change very much. So we have a basic picture now for fusion of the D2 molecule. And this was the reference problem back in 1989, 1990, through which we could think about Fleischmann-Pons results. Now, one issue is that if the deuterons get close enough to react, things happen very quickly. It's very quickly, it's such a short time that if we multiply it by the speed of light, the distance light can go is a small fraction of the distance to the next atom. And this was made as an extremely strong and effective argument that given TD fusion, relativity itself prohibits there to be any collective interactions. Namely, if you don't have enough time to let the atom next door know that you're fusing, then the atom next door is not going to be able to participate in any significant way of the fusion reaction. So a very, very effective argument from 1989. DD fusion, D's got a neutron proton, the other D's got a neutron proton. They're two nucleon objects that come together, and the product nuclei or particles are 1 and 3, neutron, helium 3, proton, triton. So 2 plus 2 comes together to make 3 plus 1 for the normal hot fusion, DD fusion. We'll be talking more about that another day. The fusion cross-section's been measured. The ratio of the D to N plus helium 3 over D plus P plus T is measured experimentally. Here's the line that's 1. The best fit has it to be slightly less than 1. And the slightly less than 1 is the Oppenheimer-Phillips effect, that there's a little bit of Coulomb repulsion that favors keeping the proton a little bit farther away from the other deuteron. Takeaway message. Well, here's the physics reason. We can understand from this model the physics reason why DD fusion is hard. We've got Coulomb repulsion pushing the deuterons apart. If we got energetic deuterons, they can go through the Coulomb barrier and fuse. They can also tunnel. The simplest model is D2, but we see that in D2 the tunneling rate is very small, the fusion rate is very small. The fusion of molecular D2 under any conditions directly has never been observed without ions. And HD fusion in the molecular case is faster. But it doesn't matter that it's faster. You've got so many orders of magnitude between these models and Fleischmann-Pons observations or other observations that were made that you can be pretty sure that whatever is going on in Fleischmann-Pons experiment is not this. Okay, let me pause. Comments, questions, thoughts? Okay. Let me talk a little bit now about the inconsistency with theory. And again, sort of going back to 1989 perspective, but the perspective hasn't changed qualitatively today. Back in 1989, there were the relevant fields of physics were condensed matter physics, nuclear physics. And the big success of modern physics is it takes what seems to be complicated problems and makes them simple. So in the area of condensed matter physics, you start out with something like palladium deuteride. You can take advantage of a Bohr-Oppenheimer separation, which takes the electronic part of the problem and the nuclear part of the problem, and it separates them. So you can analyze each one separately, and they're much easier separately. For the electron part of the problem, there are many, very large number of successes. For the phonon part of the problem, there's many successes as well. You're able to do calculations, you're able to do experiments. The calculations and experiments have a lot to do with one another. And palladium deuteride is not a particularly complicated condensed matter structure. In the area of nuclear physics is a little bit different. For condensed matter physics, most of the interactions, the Coulomb interaction, which is sort of simple. When nucleons interact, the interaction isn't simple. So nuclear physics started by trying to be like atomic physics, molecular physics, condensed matter physics, to have a simple analytic potential. In the first years of nuclear physics, a huge amount of effort was put into these pion exchange models. They calculate with them, and the results wouldn't be particularly good. Back in the late 50s, they said, well, heck with that. What we'll do is we'll do scattering experiments. We'll measure the nucleon-nucleon interaction potential. We'll fit them empirically, and we'll use that as the basis for nuclear physics. And once that was done, magically, by the time around 1960 into the 60s, nuclear physicists were able to do systematic nuclear physics calculations for nuclear structure, for nuclear reactions, began getting answers that had an awful lot to do with experiments. So by the time 1989 came along, these empirical models were developed, they were sufficiently mature that quite accurate nuclear physics calculations could be done. Note that nuclear physics is in principle described by QCD, quantum chromodynamics. And there were some early successes, quote-unquote successes, in understanding some properties of nuclei based on quark picture. So let me think a little bit about it. Here's what palladium deuteride as a lattice looks like when it's nearly fully loaded. So the palladium are the big gray ones, the deuterium are the purple ones here. So gas bottle of deuterium's got a purple top on it to give us a reference for the color. So we see checkerboard arrangement, and checkerboard arrangement displaced by one, then original checkerboard arrangement. So palladium's on black, deuterium's on red squares, move it over, and so forth. Sodium chloride structure is one of the simplest in condensed matter. The vibrational curves have been measured from neutron scattering for palladium deuteride. Deuterium's a little bit heavier than hydrogen. It's hard to measure a neutron scattering curve in palladium hydride, so the deuteride's more important for the vibrational part. When you have the structure, if you go into momentum space, you get the Brillouin zone. And the Brillouin zone is characterized by all these obscure symbols to tell you which direction you're going in. And you can use that to keep track of the different directions for these electron dispersion curves. So the idea is that for the electronic band structure back in the 80s, here's a calculation from Klein and Pickett. Here's palladium electron band structure, and here's palladium hydride. Having hydrogen in adds an extra electron, so it moves up the Fermi level, and the bands move around a little bit. There's sort of some similarities between the curves. But the basic idea is that the electron band structure was accessible back in the 1989 for these kinds of systems. Going back to, or for the electronic structure, electron structure dates back from the 30s for the case of simple metals. And for many years, it can be presented in classes and taught and in textbooks. The question is how good does it compare against experiment? Because all of the tests were sort of indirect experiment. Was it back around 1978, 79? Somebody had a bright idea, coming in with an electron beam and then doing angular resolve scattering off of it. And by doing so, you could actually measure the electrons in the bands themselves. So this is a relatively early measurement in aluminum of experimental results for the electron band structure compared against some sophisticated, I think in this case, quasi-particle calculations for the band structure. So we now know that the band picture, and we knew back in 1989 that the band picture was basically okay as long as you did appropriate calculations for the electron bands. So palladium deuteride, if you like, not a difficult system to understand from the point of view of condensed matter. You know that the bonding in palladium are due to the outer electrons. You know that hydrogen and deuterium goes into the octahedral sites, which is the ones that I showed on the checkerboard kind of arrangement, and that could be told from the neutron scattering experiments. Electron density is just right for H and D occupations we'll be talking further about following lectures. Electron density is too high for H2 or D2 formation, as we're going to talk about extensively, which basically means you would not expect any D2 to form as a molecule of palladium deuteride. Which sort of means that the D2 picture talked about earlier, even though it's unlikely, it's more unlikely that you have the D2 actually form in palladium deuteride. The D atoms are far apart from one another in the structure, so the fusion probability is much lower in palladium deuteride than in the molecule. And in a sense, there is nothing special about palladium deuteride electronic structure photon bands, or any of it, that would lead you to believe that Fleischmann-Pons ought to be seeing excess heat. Let's talk briefly. Similar arguments could be made for nuclear physics. Nuclear physics, quantum mechanical models apply. There's a kinetic energy term, there's a potential energy term. For those of you who happen, for some reason, not to be theoretical physicists, we'll talk more about Hamiltonians later on and make them simple. But this form is the basic form for a Hamiltonian for studying atoms, for studying molecules, for studying solids. And it also works in nuclear physics. The kinetic energy is sort of obvious. The nuclear potential is what I was describing earlier. People do nucleon scattering experiments. They fit the potential. In the 1980s, the Argonne National Lab 14-parameter model was one of the popular parameterizations. So the 14-parameter model had 14 different terms with different kinds of terms. There was scalar terms, spin-dot-spin terms, isospin terms, LS coupling terms, all kinds of terms. You have data, you parameterize it, you fit it as good as you can. there you go. These models were used for calculations. So, for example, in 1985, not too far away from the 1989, here's some calculations. The Reed soft core potential is one of the early 1960s potentials. The argon potential is a much more sophisticated 14-term potential. And I guess one way to look at it is to look at the binding energy. Binding energy experimentally is 8.48 MeV. The old Reed soft core potential gives you 7.35 MeV binding. The argon 14 gets you 7.67 MeV binding, and 8.48 is the right number. So if you like the models for nuclei at that time, they weren't super accurate, but within nuclear physics, at the time, this was an important result. This is evidence that you could do quantitative calculations. You could get the size, calculate the size of the nuclei, and come up respectively compared against experiment, 1.69, 1.83 Fermi for the size for helium-3, and similar kind of accuracy for the triton. Now, time has gone on. These empirical nuclear potentials have gotten better. Steven Weinberg had this bright idea of saying, well, instead of fitting it to a gazillion terms, why not specify an underlying field theory from which to do calculations systematically? So that was done. There's fitting parameters. They fit those parameters of that model to experiment. And here's results. So, for example, for experimental binding energy for the triton, 8.482, sophisticated chiral perturbation theory potential, 8.474. These numbers are pretty good. So nuclear physics, if you like, with the use of the new potential models based on empirical effective chiral theory, are quite good. In the case of DD fusion, we have two deuterons coming in. People like to draw these pictures of making a four-body excited state decaying to 3.1, but the theories are more that this neutron-proton pickup type reactions. I kind of don't think you get a Bohr state for this system. You get a Bohr state for more complicated systems. So back in around 1989, this is a calculation Jerry Hale and colleagues at Los Alamos, 1992. So we have experimental data. We've got the R matrix calculations. And you can see for DD fusion that the theory of the time was in good agreement with experiment. And it's in better agreement with experiment today. The basic issue is that nuclear physics was certainly well enough understood in 1989 to handle DD fusion. The nucleon-based models of empirical potentials were, in 1989, really starting to come into their own, being capable of quantitative predictions. They're very much advanced these days. Good description nuclear structure reactions. The few-body, three-body, four-body nuclear problems are basically solved problems quantum mechanically. Reaction models described by quantum mechanics, relatively simple quantum mechanics, really very well, and so forth. So the takeaway message here is one which is actually very powerful. We have existing theory, and we had existing theory in 1989, but it was more than good enough to handle palladium deuteride and to handle four-body nuclear reactions. Condensed matter physics, nuclear physics, in 1989 were considered mature fields. They're much more mature today. Palladium deuteride is a simple condensed matter problem. Deuteron-deuteron fusion is a simple nuclear physics problem. There's nothing special about palladium deuteride as a condensed matter physics problem that lead anyone to imagine that any anomaly should be expected. There's nothing special in the body deuteron-deuteron fusion problem that would lead anyone to believe that anything interesting should be happening along the lines of what Fleischmann-Pons claimed. The basic conclusion in 1989 was that what Fleischmann-Pons was proposing, claiming to measure in a lab, is just simply impossible. There is no place in condensed matter physics or nuclear physics for an effect of this sort. Comments?
Could you explain just very briefly what that Brilliant zone is? Is that a zone around the lattice?
What it is that if you have a periodic crystal,
Yes.
if you take a Fourier transform, you go into momentum space.
Okay.
So the directions in momentum space are described by the Brillouin zone.
But it's usually confined to
the lowest part
yeah,
of it.
but then there are multiples.
Right, of course. Of course. Exactly. Comments? Thoughts? I was hoping for more comments and more thoughts because this is one of the most powerful indictments of Fleischmann-Pons.
But one thing is that nuclear theory was applied in, let's say, in vacuum with Born-Oppenheimer hypothesis and so on, while in condensed physics we have, let's say, a different environment. Also, let's say, the velocity of speed of electrons and so on can behave differently. So the question is the nuclear theory applicable in a condensed matter physics?
Okay, a great question, and a question that I'm going to drone on about extensively in a few days. But for the point of view here, from the perspective of 1989, the nuclear physics folks would argue in 1989, as they would argue today, that what goes on at the nuclear scale, it's a scale 5 orders of magnitude smaller than for the condensed matter scale. So what happens on the nuclear scale is largely completely independent of anything that's going on the condensed matter scale. It's a little bit like saying that I'm going to go ahead and I'm going to take a hammer and I'm going to hammer a nail. Should I worry about what the moon's doing? The answer is the moon's a long ways away. The interaction's small. I'm hammering away. It takes light a second to go back and forth. For my hammering, there's no way that the moon can be involved at all. So the argument is that from the nuclear perspective, that what goes on in condensed matter physics should not be affected essentially at all by what's going on in condensed matter. Now, there are a small number of exceptions. One exception is Mossbauer effect, where the recoil momentum can be taken up by the lattice, which means you can get a narrow line width. There are other effects. For example, if you've got a beta decay and you start stripping off electrons off of a nucleus, you can change the beta decay rate, sort of for obvious reasons. So there are some minor exceptions that are known, but those minor exceptions are nowhere near enough to be able to begin to make a scratch on the very fundamental kind of statement that Fleischmann-Pons is making as an experimental observation. Namely, that there is nothing in this theory, in either fields, that would provide any starting place for trying to rationalize Fleischmann-Pons. Other comments or questions or thoughts?
Are you going to address Woodham-Larson theory at some point, or is that...
I hadn't planned on it, but if the will of the masses wants it to be addressed, I'm happy to address it.
I'm kind of curious, just because the reason that I found out about this entire resurgence of interest in this field was because Dennis Bushnell with Madison Langley talked about that as sort of connecting...
Tell you what, we'll talk about Woodham-Larson. Not today, another day. We'll talk about Woodham-Larson.
So you said you were a little disappointed you didn't have enough questions. What are the questions that, if there's one or two or three that you think would be, we should be asking about
it's,
this.
it's not one or two or three. What it is this is devastating.
Right.
Namely, if you'd like to believe in Fleischmann-Pons, and if you'd like to consider yourself to be a rational scientist, you need to take this into account. There is nothing whatsoever in the textbooks, in the literature, that can give you any help whatsoever in understanding why Fleischmann and Pons are seeing this astonishing effect. If you like, if anything, this underscores just how astonishing and how amazing that this claim is. If you like, what we're going to see is that if, well, the implication is that if Fleischmann-Pons are right, then this is wrong. Nuclear physics, condensed matter physics, has got a giant hole in it if Fleischmann-Pons are right. And given how much time and effort is gone into the construction of these theories, in terms of how much experimentation has been done in condensed matter physics and nuclear physics, nobody believes that there's going to be any, certainly no overturning of condensed matter physics and nuclear physics. But at this point, to have there be a comma changed in the formalism structure would be a big deal. But it's going to take a major revision of a foundation for this.
Are there any other holes or weaknesses or anomalies experimentally that show up, between between experiment and between these two, nuclear theory, accepted nuclear and condensed matter theory?
Your question is a great question. I'm going to misuse your question to make another point. I apologize in advance. Nuclear physics and condensed matter physics follow from some deeper theories that are more fundamental. There's, in around 1950, quantum electrodynamics was developed. Between 1930 and 1950, quantum electrodynamics was developed. So in the area of electrons, positrons, and light radiation, electromagnetic radiation, QED, the theory itself, the structure of the theory is a minimalist dream. It's got a description of the radiation field, it's got a description of electrons and positron, and it has the simplest coupling that could possibly be between them, consistent with laws of quantum mechanics and relativity. And for the past 60 plus years, there has been nothing but an unbroken string of successes in the area of QED as confronting experiment. Now there's a minor wrinkle. I've been asking for wrinkles. There's this minor wrinkle that lamp shift calculation in ionic hydrogen, ionic deuterium was done at n equals 2 levels. And it was interpreted in terms of the proton radius, which was thought to be known to 4 digits. And this came out being like 1% different. And so there's currently the world's very best QED folks and nuclear structure folks busy scratching their head trying to resolve this. There's a huge firestorm in the literature on this problem, suggesting that there might be a kink in the armor of QED. I don't think that bears any relationship to Fleischmann-Pons. You're going to need a much bigger kink. But following QED, QCD was developed, the electroweak theory was developed, it was all packaged together in the standard model. The standard model at the moment describes physics in the areas where it's applicable. It describes it basically as well as can be described. There's almost no disagreement between these models and experiment pretty much throughout all these different ranges of physics, which basically means the point that I should be making here is that physical theory at this time is incredibly strong. It's at the point where to basically settle many physics issues, you can reference these very strong fundamental theories. You don't even need to do an experiment.
And if an experiment contradicts it, then the experiment must be wrong.
You understand. You're going to be a good physicist.
You mentioned that for this to work, for instance, at the time the perception was there has to be a giant hole in the physics.
It's not perception, if you like. There has to, it has to affect.
Well, the question is, rather than a giant hole, I've heard you speak of this in the past, and you just used the word comma. And does it have to be a giant hole, or can it be terms I've heard you use, fine print? You know, and a comma, a terrible analogy would be you take 10,000 lines of code, and if a comma's in the wrong place, none of it works. And a small, revision could make a lot of things possible.
Again, the perspective here is still back 1989. So, circa 1989, there is no obvious way forward. I'm certainly going to be talking about ideas about theory. That's going to be, we're going to be building it up Tuesday, Wednesday, Thursday. So Thursday will be the big day for talking about fine print and so forth.
Didn't things get even messier when people started getting XSE for nickel hydrogen systems?
That was 1990 was the first one. Yeah. but we're being negative now. We haven't gotten more takeaway message. Cold fusion as a real experimental effect would imply that we, the collective we, do not understand condensed matter and or nuclear physics in some very fundamental way. But we're missing something very basic, very fundamental in our models. This is a scenario which was not seriously contemplated in 1989, 1990, and it's a scenario that's not seriously contemplated today.
I mean, this is in spite of seeing excess heat from experimentalists all over the world. I mean, there's work done in Israel, there's work done in...
You wouldn't be talking about all these discredited experimentalists. We'll come to that.
There have been other major revisions to our understanding of science. Is the required change to our thinking, how would that rate on a scale compared to other major revisions of science that we've seen?
Your question's a fantastic question. The thing I look at is, within the last century to quantum mechanics was the big philosophical, conceptual, mathematical change in our understanding of how the world works, and that took generation or two to fully come about. Our understanding that's needed here is of that general scale. I mean, the anomalies that we're seeing are fully as serious as those that were faced by Einstein and Schrödinger and de Broglie and Dirac and so forth. So this is big. This is very big. The implication of these experiments is very substantial and is going to require a fundamental revision in our understanding, if they're correct. I'll be, have to be worried about relying on experimental results from discredited scientists. We'll talk more about this. Skepticism. So back in 1989, this was on the radar screen. It eclipsed all other stories in science for a month or two. There were cartoons. This is excess energy generation. You can tell where the excess energy is coming from. I had referred earlier to Huizenga's impartial account of his investigations in cold fusion and the DOE RAV thing. He encapsulated what he viewed as being the big issues, the theoretical issues in his three miracles. One, how can the Coulomb barrier be overcome? The answer, of course, is the Coulomb barrier cannot be overcome. Two, the branching ratio miracle. Even if you get two neurons together, you'd expect the 2 + 2 to go to 3 + 1. So how do you make that be different? And the answer is, of course, there's no way in the world you can change the branching ratio for the conventional D + D fusion reaction. And the concealed product miracle, that if somehow helium-4 is produced, so the arguments made back in 1989 was that probably helium-4 was a product. In fact, we didn't find out till later, but Fleischmann had experimental evidence that helium-4 was being made. So according to Huizenga, the issue is that if you can make helium-4, normally you get a 24 MeV gamma. Somehow, you got to absorb or deal with the gamma. So how do you arrange for that? Well, the answer is you can't. If you make a 24 MeV gamma, it's going to go out. And there is no way to absorb it. From my perspective, looking back, Huizenga didn't go anywhere near far enough on this one. Huizenga's focus was on the 24 MeV gamma. But looking back based on what we know today, Huizenga is an amateur with respect to being a skeptic. I mean, the argument with respect to the gamma, there's no gammas, there's no neutrons, there's no charged particles, there's nothing energetic with an energy exceeding something in the general neighborhood of 10 keV. And how do you explain that? So Huizenga's third miracle here, in my view, doesn't go anywhere near far enough to capture the real problem here. Kuhnen attributed the experimental result to the incompetence in illusion of Fleischmann and Pons. There's a quote in Taubes about Will Happer and incompetent boobs, as I recall. Maybe one of these days I have to go dig that up. And we have from nature, no less a source in science of nature, cold fusion discreditable to the scientific community as a whole. First, it has licensed magic in the particular sense of a remarkable phenomenon. Could be unicorns next, claim equal credence even when they find face of expectation. Shown up in the frailty of collective confidence in theoretical science, why else should so many serious people be bamboozled for so long? 1990. Sir John Maddox. So the excess heat effect of the Fleischmann-Pons experiment was judged. The soul of the effect was weighed against a feather and was found not to be real by the appropriate scientific and governmental bodies. Of course, a wake was held at MIT at the Plasma Fusion Center. So the comment says, don't you remember? Herb and Sally and Herb said he knew a way to get fusion to work at room temperature using only gin and vermouth.
One of the problems, by the way, for the phase 2 experiment, I know we disagree on that. One of the things that bothers me is that they had 2 notebooks for that week before that, and they got the excess heat. I know Peter disagrees, but they got it 4 days before that party. So what do you do when you put the signs up and then you get the excess heat?
Okay, so cold fusion was killed. It's dead. Thank you for your attention. Questions?
I got a question. That first point you put up with the Coulomb barrier. How do you
way back? I'm going back.
It was your last.
Keep going.
No, go the other way. It was the last thing that the last topic. You had a bunch of things and why they couldn't. Why
The 3 miracles?
Yeah, that's right. Why this couldn't work. That's fusion rate miracle. Now, I read some paper that talks about electron screening, which reduces that barrier. Will you talk about that at all?
Yeah, I'm going to talk about it. I'm not going to talk about it now, but I will talk about it. Basically, low energy beam experiments have been done that shows a substantial screening effect. And the screening effect, even though substantial, is nowhere close to what's needed to account for excess heat in Fleischmann-Pons experiment.
the Widom-Lawson theory, experiment number 3.
Widom-Larson theory wasn't available in 1989, 1990. We'll talk about it. Based on the will of the masses, we'll talk about it later this week. Other comments or questions? Probably some of you know I'm not done yet. More takeaway message. Takeaway message. Good scientists, good laboratories put in a lot of time and effort trying to get confirmation XOC. They failed. I've now emphasized how big of a deal the existence of the XOC is as a challenge to modern science in the area of condensed matter and physics. Huizenga's miracles encapsulate the basic problem. The strong implication from all of this is that the experiment must be wrong. Back in 1989, measurements of neutron emission in connection with excess heat experiments were done. The argument being is that if you have fusion, normally fusion would get you neutrons, so you can figure out how much energy you're making by measuring the neutrons from the cells. So people put upper limits that were 10 orders of magnitude lower than the watt level based on neutron measurements as a way to do calorimetry. Fleischmann-Pons and others were attacked. All experiments, all theories, and basically all scientists in the field were discredited. So here's my takeaway message. Time for me to catch my breath. Comments?
So why wasn't there an implication that the experiment might be right and it's not cold fusion, it's something else, it's some chemical type of...
Well, we've argued that the amount of energy is so large and the absence of chemical products rules out any chemical explanation. Namely, if it's real, it has to be nuclear.
So presumably around that time, Andy, you were minding your own business and research in other fields. So for both you and Dr. Swartz, what your takeaway message for you gentlemen in 89? Why did it hit and stick for you?
Your question's a great question. I can't speak for Mitchell, but for me, my colleagues at MIT and my colleagues at Livermore, where I'd worked previously, knew that I was a multidisciplinarian, and they said, well, you know, nobody's going to work on this, and it's going to be discredited, and it's going to be, Fleischmann-Pons are going to be, taken out in the back and shot. So they said somebody needs to work on it and figure out what's going on. So at Livermore, I was out the day after the announcement to do some consulting, and my boss said, "Well, if you want to get paid for your consulting, you got to figure out how it works." My judgment on it at the time was that that for an experimental claim of that sort, it was going to take some time to sort out. It was clear that it was going to be knocked off the radar screen in a hurry. It was clear there was going to be politics. It was clear that the skeptics were going to win the first round. But I was interested in the question as to whether it was real or not. And for the first 4.5 years I worked in the field, I had no idea whether it was real or not. In fact, to be honest, I thought it was wrong. It took years for me to be convinced that there was something to it. And that only came by talking to experimentalists, going to the lab, looking at data, going to conferences, and again and again and again and again. Finally, it became it became clear to me that there was something real there, but it took forever. Others understood it much faster than I did. When you come from a physics background, you tend to believe the world should work the way that you study physics, and it's not an easy thing to contemplate that there might be something else happening. And I've said this a dozen times. If this effect is real, it's a major challenge to our current understanding of condensed matter nuclear physics. And such a possibility was not seriously considered in 1989, and it is certainly not being considered within the scientific community today. Okay, some of you know that I was going to go on a little bit further. There were results past Fleischmann-Pons. There are a lot of positive experimental results were obtained at a large number of institutes. Sadly, the number of institutes involved now is a pale shade of what it was in previous years. There's almost no resources today, so there's very few people left in the business now. Here's an early experiment from SRI. Mike McCoubrey at SRI was a postdoc for Martin Fleischmann and had great respect for Martin Fleischmann. And at SRI they got some funding and they set up a cell. Mike had this, we're going to talk a little bit about the electrochemistry, but we're going to find that the loading of the cathodes need to be treated gently. To get an excess heat event to occur, you need to do something to it. Mike's way of inducing an excess heat event was to make use of a current ramp. We're going to talk a lot about this, the associated ideas shortly. In this case, a current ramp was implemented. So here's the excess power that responded, namely, as soon as the current ramp was initiated, and from this plot it almost looks like the cell seems to be anticipating the current event, but I don't know that that's quite right. We get an excess heat event, and then the excess heat event goes down. Even though the current's sort of still ramping up here, it's starting to come down. The amount of excess power here, 1.5 watts, and of energy produced is 8 watt-hours. This is an early positive result. At IMRA, Japan, this is a little bit later, 1994, an extensive set of experiments were done in a fuel cell configuration. Basically means you put an overpressure of deuterium gas. Excess heat was observed, but it was found to require a high current density. So for example, here's 100 milliamps per square centimeter. Once you hit a threshold, it goes up. And note that the CalTech experiments, that was one of the major negative results, was that a current density not exceeding, well, they didn't make it to 100 milliamps per square centimeter, for example. So if there was a current threshold, they certainly didn't find it in their experiment. Ed Storms, working at LaSalle, I apologize, Mitchell. Ed Storms did an experiment, saw excess heat, and this is watts. Here's 5 watts of excess heat. This scale is hours from the beginning of the electrolysis. This is 220, 240 hours. Basically, in Fleischmann-Pons experiment, they needed on the order of a month before an excess heat event would be seen. At SRI, 3 weeks to a month before the excess heat would be seen. And a long time before excess heat in Storm's experiment. There was a lot of criticism of the isoparabolic calorimetry used by Fleischmann-Pons. In response to that, SRI built a flow calorimeter. The idea is that flow calorimeter would be sort of easier to understand. Namely, you flow water in, it wanders through the calorimeter, it flows out. You measure the flow rate, you measure the temperature change. All the heat goes into the water, almost all the heat. So 99+% of the heat, roughly 99% of the heat goes into the water. And the heat capacity of the water is well understood, and you can get an accurate measurement from flow calorimetry. So it doesn't suffer from the headaches associated with isoparabolic calorimetry. It's also a closed system. People were arguing in the Fleischmann-Pons system that gas was coming off, so if you had recombination, you could account for all the excess heat from recombination effects. Of course, a factor of 20, it wouldn't be possible at all. But people said it, and it was believed back in 1989. In the early 90s, early to mid 90s, there were about 40 observations of excess heat events with this flow calorimeter. And once again, we have a current profile goes up, and I get an excess heat event, which goes up in connection with the current. You have excess heat in heavy water. In light water, you see either a much smaller effect or no effect in these early experiments. Mitchell's going to talk to us about his experiments, but here's a result from one of the fuser experiments, electrochemical experiments. So factors of 2 and 3 excess heat were seen in the fuser experiments, which we're going to get the pleasure of hearing about shortly. And energetics in Israel, a current protocol was used. They call it super waves. Complicated current profile. I think it's a super wave all about. I tried to explain it to my friends. Okay, you want to know what a super wave is? It works like this. Your desk drawer is stuck. You're trying to open it. What do? Go down, you pull it. Nothing happens. So you pull it harder. Nothing happens. That's a super wave. You rattle faster when you're at higher amplitude. And that's found to increase the loading. And in connection with the increased loading, results like this were observed. So in this plot, here's 0 watts, here's 40 watts, here's the input power, here's the output power. The output power is on the order of 25 or 30 times larger than the input power. This kind of effect was observed in 5 or 6 experiments at energetics. More typical behavior is that they would see factors of 2 or 3 excess power. When you've been in the field for a while, you say, well, you see enough presentations of excess power, and you say, well, excess power is real. You know, let's start asking questions. Can you turn the excess power on? Well, the SRI current increase protocol appears to turn the excess power on. Dennis Letts found that you could turn the excess power on by shining a laser on the surface. This is an experiment aimed at trying to do some physics. So 2 lasers are shined onto the surface. And the frequencies are slightly different between the 2 lasers. In this experiment, the 2 lasers are turned on here. The excess heat turns on in response. And in this particular experiment, the lasers and the excess heat remain on. In the 2 laser experiments, the excess heat remains on even when the 2 lasers are turned off, at least for a while. So this shows some degree of controllability. We can do something and we can turn it on.
That's just not just radiant heating, the laser's heating it up, is it?
Reviewers argued that that's exactly what was happening. With 2 lasers, the energy was being absorbed, and that would cause the power to increase. So I calculated the reflectivity, and I estimated that under these conditions there ought to be 15 milliwatts of laser power absorbed in the cathode. And so the total effect here is 300 milliwatts. So it's a factor, the thermal response is 20 times larger than the incremental excess power. And we found some negative results where the calorimetry was good enough to measure the power absorbed by the lasers. And when we looked at it, it was 15 milliwatts. And Dennis said, how'd you figure that out? Well, theory actually works sometimes. There was a demo done at MIT. There was a number of demos done at MIT. This was done in connection with ICCF 10. This is John Dash. He brought some students who had done a cold fusion demo. And so there's the demo, and there's one of the students. So he saw weakly positive excess heat results at that time. At the same, in the same room at the same time, Mitchell was carrying out a demo. That orange door was the door to my office. This is the outer office of my area. So Mitchell will talk more about this experiment, but he saw a factor of 2.5 excess heat. So takeaway message. There have been positive results subsequently in Fleischmann-Pons experiment. Positive results at many labs. Positive results on different kinds of calorimetry. So isoparabolic, simple thermometry, there's flow calorimetry, Seebeck, Lavoisier, phase change calorimetry. And this motivates us to try to understand the experiment better. And also, we're scratching our head thinking back in 1989, 1990, there were a very large number of experiments done at the laboratories by folks by good people, who didn't get positive results. So something we're interested in is why in the world was there so little success back in 1989, 1990? So take away that slide. Comments or thoughts?
Why all experimental setups are so small volume? Because if, let's say, the volume is bigger, maybe the effect is so big that it is not possible.
I can give you two reasons back in 1989, 1990. One, palladium's expensive. The other reason, heavy water's expensive.
And one more thing, time constant. If you do an experiment, you might want to have, when we did the first aqueous one, we had Gene Mallett come over, saw the control, he came back the next day and saw the excess heat, which he told me to come bring here, and we did. But even there, with 40 cc's, we had a time constant of a day. Okay, so if you're talking about hundreds of cc's, you've got two issues. One, the heavy water for my experiment runs $3,000 a liter. That was enough to stop me. And the other one's a time constant.
Okay.
How about the metal itself?
So at this point, we've gone through the introduction, and I'm trusting that the introduction has gotten you guys oriented to the kind of things that are at stake here. So we have at stake the future of the world. We have at stake giant holes in condensed matter physics, nuclear physics. We have at stake the way science is done, the credibility of the scientists themselves, and the process by which science occurs. So with that as introduction, we're going to now turn our attention to technical issues. Technical issues. I had argued before on one slide which went by very quickly, so that there's known science, there's new science. Clearly, to understand Fleischmann-Pons, we're going to need to encounter some new science, some new physics, some new mechanisms. I don't want to start there. The place where I want to start is I want to start by saying that, look, there's an awful lot of science that's very well known and that apply to these experiments. So what I want to do is I want to start building up a foundation upon which we can understand the basic Fleischmann-Pons experiment as an electrochemical experiment, as a physical chemistry experiment, as hydrogen and metals experiment, and so forth. So this is basically, I think we need to do our homework before we can have an intelligent discussion of the experiment itself. And the place I want to start is with lattice expansion. So the fact that you could put hydrogen and deuterium was figured out by a fellow named Graham back around 1866 or so. And basically, you take a piece of palladium, you put it in hydrogen gas, and if you cook off the oxide surface, then the hydrogen will go in. You have to heat it up in order for that to work. And when it goes in, the question is what happens? Well, one thing that happens is that the lattice expands. So this is concentration of hydrogen or deuterium per palladium. So here's 0.6, 0.81. So the 1 corresponds to the nice, everybody filled in all the slots, the H to D or H to PD or D to PD loading is 1. The lattice constant is 3.89 angstroms, which is down here somewhere at 0 loading. And this number is somewhat north of 4.08 angstroms. And so for example, in some laboratories, people check what the loading is by measuring the lattice constant. Because the more hydrogen you put in, the more the lattice stretches out. Now the lattice constant, the change in volume between fully loaded palladium deuteride and palladium goes like the lattice constant cubed. And it's 4.08 over 3.89 cubed, which is 1.15. The volume increases by 15% loading it fully. Does that strike you as being like either interesting or big effect? For example, how would you feel if your volume were increased by 15%? This is huge. This is one of the most stunning thing you can do to a solid, to increase the lattice constant, to increase the volume by this much. Palladium hydride is not unique in this. For example, here's tantalum hydride, tantalum deuteride, and once again, this is increase in lattice constant as a function of concentration at much lower concentrations. This is sometimes understood as a simple volume increase for hydrogen going in. Namely, you put a hydrogen in, it pushes the lattice out locally, and you can assign a volume to hydrogen going in. So in the case of palladium, it's 2.8 cubic angstroms. Tantalum, 2.8 cubic angstroms. Niobium, 3.13 cubic angstroms. So this is a common effect in metals, the lattice increasing. It's just that in palladium is one of these unusual metals that you can put hydrogen in, take it out, and it's sort of reversible.
Do people use that change in volume as a diagnostic for the concentration of hydrogen?
Yeah, people, there's a lot of literature on people measuring the lattice constant as a way to diagnose how much hydrogen or deuterium is in the solid.
Have there been any attempts to load palladium or other metals while constraining their dimensions? So for instance, not allowing it to expand 15%, will it load, will it not load? Do other effects take place?
A great question. At issue is how would you do that? So for example, you can imagine putting stuff, holding it together, and then you load it and it pushes. Well, the amount of pressure that corresponds to this kind of volume increase is phenomenal. I'm talking about gigapascals. So basically anything you'd hold it would get pushed back on with equivalent pressure. Although I suspect you can do some constraining, I think you're limited in your ability to constrain the volume here. I guess people have done experiments where you've shocked it, you can squash it, but that's not really a static constraint. Takeaway message. Loading deuterium stretches the lattice, huge effect. We'd expect an increase in the elastic energy. Namely, if you put all this hydrogen and deuterium in it, pushes the lattice apart. It takes energy to do that. So the more you stretch it, the harder you have to push the deuterium in to get the lattice to expand.
And you said it's reversible, so that energy will come out if
you can
comes out.
get some of the energy back. Of course, some of it's not reversible because there are changes in the microstructure. You never get that back. This also is one reason why the electrochemists tend to treat the loading of palladium with deuterium or hydrogen. It's sort of, the cathode's very gentle. So if you put the palladium in too fast, the volume increase is very rapid, and it's going to do bad things to your cathode. So, for example, SRI, they take forever in a day. They load a little bit, they load a little bit more, give the lattice time to stretch out, reorient, and not be destroyed. Namely, if you load too fast at SRI, what they noticed is that the cathodes would just develop a crack, and with a crack, all the deuterium would just go out. What's the analogy? Would break like an overripe banana or something. Phase diagram for palladium hydride, which is similar to palladium deuteride. Okay, so this is loading. Here's the 0.6. Here's 20 degrees C, which is near room temperature. So you imagine a piece of palladium in hydrogen gas, you got rid of the surface oxide layer, you turn up the pressure, and what happens is when the pressure reaches a little bit less than 0.01 atmospheres, the palladium just absorbs, it sucks up the hydrogen freely up to a loading of about 0.6. And then at 0.6, if you want to crank the loading up, you've got to crank the pressure up. So if you want to get to 0.67, you've got to be a tenth of an atmosphere. If you want to go to 0.72 near room temperature, you've got to be 1 atmosphere. And it goes up and up and up and up. If you want to get to a loading of 1, you've got to be over a gigapascal. So gigapascal, atmosphere is around 10 to the 4th Pascal. So it's 10. It sounds like too many atmospheres, but call it 10 to the 5th atmospheres. Here's the difference between hydrogen, deuterium, and tritium. So to get equivalent loading, basically deuterium, it's harder to put deuterium in. You have to be at higher pressure to get into the miscibility gap in the case of deuterium. And tritium is even higher. This is completely well understood. It has to do with the 0 point, primarily to the 0 point energy of the molecule.
I'm sorry, I missed it. What is the difference in the volume expansion if you use deuterium or tritium?
They're very similar.
So it's more a case of getting it in, and they don't necessarily elbow out more room, but it's just harder to get it in.
Yeah, and it also means that if you've got a mixed material with deuterium and hydrogen, that the hydrogen wants to go in more than the deuterium does. And this actually gives you a physical basis for separation of hydrogen, deuterium, and tritium. So this is one of the ways that hydrogen is separated from deuterium. Deuterium and tritium is separated from hydrogen. The notion of chemical potential will be important to us. Probably some of you are thinking back, chemical potential, and you're remembering like bad days in a chemistry class years and years ago. But what I want to do is I want to make it not be so bad. So chemical potential is going to be some constant offset. And then, in a sense, it goes like the log of F. What the heck is F? F is fugacity. Well, fugacity is sort of like pressure. So here's for hydrogen, here's fugacity as a function of pressure, and this is a straight line below 1,000 atmospheres, and a little bit of a deviation going up to 10,000 atmospheres. So basically, if you know the pressure, then you can figure out the fugacity. You can plug in this formula and figure out the chemical potential for deuterium or hydrogen. So what that means is that if you take the loading data as a function of pressure from the phase diagram, you can figure out the chemical potential. So here's an example of pressure versus loading. So this looks like deuterium. So here you go to the miscibility gap. Then your pressure increases, and so here 10 to the 4th atmospheres, I screwed up an order of magnitude, 10 to the 4th atmospheres gets you to a loading of 1. But given that I know the atmospheres, I can figure out the fugacity, which means I can figure out the chemical potential. And here's the chemical potential. Chemical potential is relative. If I call 0 the miscibility gap, and then the chemical potential goes up linearly. Looks like it goes up a little bit in this model. This is a loading of 1.2. It kind of goes over. And it's 100 millivolt, 200 millivolt, 300 millivolt. So these are big numbers for chemical potential.
Physically, what's going on if you have a loading overload?
Basically, in the experiments where this was taken from, the diamond anvil cell was done. Once you run out of octahedral sites, you got tetrahedral sites where your hydrogen goes. So there's twice as many tetrahedral sites as octahedral sites. So if you fill them all up, you get to a loading of 3. Of course, that would require a lot of energy. Now this chemical potential actually shows up in the experiments. And here's some data of storms. And he did loading and measured the open circuit voltage. So after he loaded, he stopped the electrochemistry and in a short time measured what the residual open circuit voltage was. So what happens is this curve is a little bit flat, and this curve goes up, straight line, and the slope of this line pretty close to the slope for the chemical potential, because in this particular experiment, the change in the open circuit voltage is actually associated with the chemical potential of deuterium inside. The thing that I want you to understand is that this increase in chemical potential, it's a big deal. And what it means in practice is that you have to push harder to get more deuterium in at high loading. That it becomes, if you like, exponentially harder to load at high loading. So next lecture, that's going to be a key issue, which we're going to focus on. So palladium can absorb hydrogen, deuterium, tritium from gas, more pressure, more loading, easy to load up to 0.6. Your temperature becomes exponentially more difficult to load above 0.6. And this notion of hydrogen and deuterium chemical potential in connection with the loading is going to be a concept that will be important for us as time goes on. Okay, I've babbled for 2 hours. Mitchell's going to give some discussion. And I'm wondering whether we have to take a bio break. What's the will of the masses?
Yes.
Okay, so we'll resume in 10 minutes.
Today we talk an overview of materials. We'll talk about the dielectric response of materials to an applied electric field intensity. This is important because if you want to successfully activate either an aqueous cold fusion system or a nanomaterial cold fusion system, you know really what goes on with polarization and conduction and pathways that tend to quench the desired reactions. You're going to find that people failed in cold fusion not only because of loading, but because there are many pathways that shut off what we want. On day 3, we'll talk about the nanomaterial systems. These have been incredibly successful. I'm going to show the first ones here. These are what we showed at the demo. We'll let you come up later and take a look. These have the nanomaterial in them, so it's no longer even in a water bottle. It looks like a resistor. We're able to put an electric current through, and we get excess heat out. On day 4, we'll talk about the magnetic, optical, ionizing, radiation, and ultrasonic effects, and then the nickel systems. I happen to believe there are successful theories in cold fusion. I use a lot of them. Take a photo, yeah. Basically, this isn't gonna, I need a way to point. The most successful theory I use is the quasi-one-dimensional model of flow. I use this as a replacement for classical electrochemistry in the Nernst equation. Later today, we'll talk about the limitations of conventional electrochemistry. And this particular model has been very successful for me because from this we've been able to generate co-deposition, the CAM effect, optimal operating points, a whole number of things come out here. This is the introductory course to cold fusion. If you see things in black, this is an advanced course. We'll discuss that there. But we're going to try and cover everything that's not green in the next few days. So today, we'll do the overview materials, dielectrics and electrochemistry. Basically, we'll talk about what the skeptics did. That's why I put the slides up. Why don't we just get into that? Why it's important. We need energy. We use a lot of it. Most of it is from non-regenerable materials, dirty materials that create a lot of negative effects, like pollution, and cause other kinds of problems that we don't have to go into here. So what do? We looked at cold fusion. And the alternative, of course, is hot fusion. That's where all the money goes. And the question is, what can we do with cold fusion to get to the end of the tunnel? You know that the fuel is hydrogen. It tends to, we're not sure if it's protium or deuterium with nickel. It could be both. It's apparently deuterium in the palladium. And our product, for a number of reasons that Peter will discuss in detail tomorrow, is helium-4, and we see that it's both its total amount generated and the rate of production are consistent with generating helium-4 in a commensurate way. Excess energy is defined as when we have a resistor and we put a current in through it, we have a voltage across it, we take the product of the two, that gives us the power in watts. And if we integrate that over time, we get an energy. When we talk about the term excess energy, we look at the heat we get out, we subtract off the total energy that we put in, and that's what we term as excess energy. Now, we always use ohmic controls. One of the things I'll show you in the next few days is we use a lot of controls. We use ohmic controls, we use calorimetry controls. But an ohmic control, when I refer to it, is where we take the calorimeter, and then in place of looking at the cold fusion device, we put in an ohmic resistor, like a carbon resistor or a wire wound resistor. And that gives us what the conventional 100% energy dissipation is. And any energy that we see coming out beyond that is what we call excess energy. A nanor type device is where we take an active cold fusion material, usually that's dry, we put it in a tube, and we have two wires going in, and we call that a nanor. And we use that for a number of reasons. One of them is that a lot of the nanomaterials have danger. Biologically, nickel is not well tolerated in the body. Gold, platinum, and palladium are, but not nickel. Okay, so why is cold fusion important? One, there's an abundance of protium and deuterium everywhere. And if we take deuterium out of water, we're left with clean water. So there's zero carbon footprint, there's no residual radiation, there's no radiation coming out that's ionizing and penetrating. There is radiation that comes out, there's heat, which in fact is radiation, but what we mean is there's no ionizing penetrating radiation coming out. And the other thing that's important is the energy density, as Peter began talking about. So one, why not go for this? It's everywhere. Two, there's nothing as clean as cold fusion out there. And that's why we have a single opportunity to take care of it. Now, in terms of looking at the energy density, here we have a number of materials. I hope you can read that. Here are conventional fuels, gasoline, ethanol, coal. These are foods we eat. You notice that if we draw over here where TNT and dynamite are, we actually have a higher energy density in our donuts, which is probably why we love them so much. But the fact is we burn it slowly. And so the net rate of power coming out with a donut and butter. These are the energy foods, you see. They're all higher than TNT and dynamite. But on the other hand, cold fusion is even out even farther. Now, we're not as far as the theoretical limit. This is actually what we measure now. So, for example, if we look at cold fusion systems, and we look here at energy density, and we look at power density here, I plotted up conventional energy production systems, supercapacitor, lithium-ion battery, and here's our NANOR way off over here. That's why we're chasing it so hard. And obviously the corollary of that is few things are as efficient as cold fusion. Okay, so let's go to the next one. Any questions?
Actually, Mitchell, just really quickly, you talked about power density and energy density. Were you talking about them in the traditional sense of watts per unit volume?
Yes,
volume,
exactly.
As opposed to specific.
Exactly. This is conventional sense for a given amount of volume. How much power can we get out? Carl wants to get out 60,000 watts for his flying car, and we'd like to supply it. And right now we need 60,000 nanos. So we got to get to work. Okay, so let's just briefly talk about the materials. You're very aware of these, so we'll skip over it. I think where I'm going to spend a little bit of time is with the water. And that's because tomorrow we're going to talk about aqueous systems. And one of the questions was how we got into this. In '89, I had been working actually on the floor above here, right above this room, with Arthur von Hippel looking at water from 1967 to 1971. So I had a lot of interest in the effect of putting an electric field intensity on water and its interaction with platinum and palladium and other materials. And I actually went into this to prove it wrong. And to my surprise, when we applied the system that we had developed for a different reason, and we'll get into that tomorrow and Wednesday, I was left with the fact that we were getting excess heat. And so I followed it ever since. Okay, what materials are needed? I'll just briefly show what some of our results are. With our palladium systems, this is what we've measured in aqueous systems. In the nanomaterial systems, we've had energy gains as high as 40. At the IAP course 2 years ago, we got an energy gain of 14. These are our nickel results. We'll go over these in detail later, but I just want to show you briefly what it is. We've never seen excess heat with these other materials. Sometimes we use chemical controls, where instead of a cathode of palladium and instead of an ohmic control, I'll put in a piece of aluminum or other materials, and none of these have even come close to showing excess energy. But it is a good control you should use. Okay, so our goal here is to figure out how we're going from hydrogen to helium using nickel and palladium. And what we're using for electrodes are platinum and gold because they tend to be corrosion resistant. They don't have hydrogen embrittlement. They have a low hydrogen overvoltage, and we'll go over that in a minute. You've seen all of this stuff. This is hydrogen on top, deuterium on the bottom. Deuterium has a nice pink color when it's ionized. We can just skip all of this. The important thing is hydrogen, deuterium, and tritium have very different chemical effects. And they probably have, and of course, all we have to do is get through the Coulomb barrier. And this is, as Peter was talking about before, most people in hot fusion like to use PT because there's a greater cross-section, and we're down here using this. Okay, water. What is water? One of the big problems we have is that in this field, people talk about we use light water. We're not using light water. We're using ordinary water. So 1 in 6,000 or so of the hydrogens in the water are going to be deuterium, and that's a definition of ordinary water. I don't know of anybody that's ever looked at either nickel or palladium with light water. Is that right? I don't think anybody's ever. There was one? We could find out what happened later. Okay, and conductivity water is a misnomer. When we get water that has no additional ions in it, And before it becomes in equilibrated with the air, the resistivity is about 18 megohm centimeters. And that high resistance water is usually called conductivity water. Okay, so we have water, and the question is, why does it do what it does? And the interesting thing is, we could talk about thermal conductivity, which we will later, and expansion issues, and pH. But the real interesting things are, why is the specific heat so high? And why is the dielectric constant so high? Anybody?
It's polarizable.
Huh?
Polarizable.
But that's it. A lot of things are polarizable, but they're not that high. So let's talk about, because I think this is really important in understanding what's going on. We can skip this. This has to do with the fact that the polarizability, the dielectric constant of water is so high that if you put a electric field across, I think this is a few kilovolts, or this is at 400 hertz AC, the water rises because the total energy of the system goes down by having the water in the place. And the only reason it goes up is the fact of the high dielectric constant. Okay, so water actually is very close to a solid. Only 1 in 7 hydrogen bonds are broken. When you leave, the important thing you should think about is it's very close to a structure. You should think about, when I get done showing you, why it has a high dielectric constant. How do protons and deuterons move through it? And then what you're going to see is we're actually dealing with 4 lattices here. There's the palladium lattice, there's the deuteron lattice within the palladium, there's actually 2 lattices here. There's an oxygen lattice, and as you'll see, there's a deuteron lattice that's inscribed within it from the applied electric field. In order to understand water, we've got to look a little bit at the phases of ice. Water is actually a sum of essentially ice 1, ice 2, and ice 3. And if you want, any of you that want a copy of my paper on it, I'll send it to you tonight after the class. But basically, the hydrogen bond to water is so high that you end up having about 4.5 kilocalories per mole. They're very hard to pull apart. And this is going to play a big role, I think, in cold fusion and how we load. We can skip all of this. Basically, the structure of water is there are these hexagons. There are 2 types. If they overlap, it's a word. This is ice 1H. And the important thing is that there are these long channels that the protons do not go through, but ions can go through. And here I took a cross polarizer off one of the ones that I built. And you can see the
Eventually, you have to explain to us your moving graphic.
Yes. I'm trying to find something. That's what it is. Here we're just looking at the oxygen lattice. I think the issue here is there are many ways that these lattices can form. Water is essentially ice 1 with a little bit of ice 2 and ice 3. This is ice 1. This is still ice 1. Here's ice 2. The dielectric constant goes away in ice 2. And I'll show you where it comes from in a moment. Here's ice 3. There's a lot of different structures. If you cool it way down, you end up going to ice 9. Now remember, this would be decorated with protons on here. And I'm not showing that now. I just want to show you the diversity of the structures. And again, the important thing is just to understand it's there, because we're going to end up using it in a moment. This is heavy water. I showed you there's one over here. This has been the big problem we've had with doing experiments in aqueous systems, is if you run a cold fusion cell and end up boiling off your heavy water to the air, you got to replenish it. And at $3,000 a liter, that's been a problem. And not all heavy water is that. This stuff runs about 200, 300 a liter. We use low paramagnetic heavy water because we don't want any ions in it. And I'll explain to you tomorrow what's going on. We can skip all this. I know, you know all the stuff about palladium. And we've already talked about the load. I got to get through this. This is just an introduction. Think of this as a survey of things that you can go home and study. The important thing is not only the loading, but the total capacity of how much hydrogen we have in. And palladium is important because we have a lot of carrying capacity compared to other materials. I mean, here's a 10,000 psi container. I lost this again. Okay, the reason the loading's important, as Peter will show you tomorrow, people who have low loading below 80.83 don't see excess energy. And when you go above 0.83, 0.9, there's a quadratic coming up, the excess heat coming up. This is one big important issue. Now, the palladium is important, as Peter mentioned, because hydrogen can get through. What's really interesting is this: if it cracks, hydrogen gets through faster, but you lose the selectivity. Okay? We find that there's a lot of talk on the internet about cracks being important. In every experiment I've ever run, cracks ended. If you have a crack, you lose the selectivity and you lose the excess heat. And as Peter pointed out, the permeability of palladium isn't the highest. Other metals are higher, but these have hydrogen embrittlement, and the palladium doesn't. You can get away by putting the hydrogen in a foil, taking it out, putting it in. It'll look like a little bit of crumbled aluminum foil, which will look better and better as you put more silver in.
What do you mean about selectivity when you lose selectivity?
Selectivity means if you want to pass a series of gases through, let's say we take hydrogen, CO2, O2, only hydrogen will go through until you crack it. Then they all go through. You lose that selectivity, which is the advantage of the palladium to begin with. One thing I really want you to think about is palladium is an M4. E-M-P-H-O-R-E comes from the Greek amphora, meaning vase. And just as in medicine, we talk about hemoglobin as binding 4 oxygen molecules and then taking it into the body and releasing it as a vase, it's really critical to our life, hemoglobin, just as other M4s are also important. There are molecules in the body that bind thyroid hormone, that bind iron, and if you don't have transferrin and thyroid-binding globulin, you won't live. What happens here, which is really interesting for me with palladium, is there's a massive decrease in solubility as you raise the temperature. I think this is the reason why palladium is different from the other metals. And we'll talk more about that later. I think what happens is when you get a local temperature increase, you're going to deload all of the palladium locally. And now, where's that proton going to go? Where are those deuterons going to go? And I think they're going to head to a vacancy, and we'll talk more about that later. When you put in hydrogen into palladium, you destroy the structure. This is an X-ray spectrum that Peter and I took, I think back around 2006, 2007. Here is the spectrum. This is a result of the measurement. It's removed for the calculation. But here you see a nice lattice until you load it. And once you load it, you destroy it. So loading itself has a bad effect. Palladium has one other interesting effect, which is unlike all other metals, when you look at the EMF versus metals, it's the only one that goes down. You were looking for differences. I have a lot of interest in the structures of the lattices, both with respect to vacancies, which we'll just mention but not really talk about today. Peter will talk more about it later. And dislocations. This is dislocation in graphite. And vacancies we looked at back in the 90s by the result of irradiation of electrons. What I did basically is took palladium and nickel electrodes, put them in front of the Van de Graaff here at MIT, and gave them the dose of about 300 gigarads, which was just enough to put lots of vacancies into the metal and set the wood underneath it on fire. And so here at 300 megarads, we're getting massive amounts of changes in resistance. This is the defect density. As Peter mentioned, there's an expansion of the lattice. We measured that too. And here we see a quake. These are changes in the temperature, and here we see a resistivity quake. The reason I mention this as being important is I think the vacancies are where we get the active site. And I think we generate these when we do co-deposition. So for example, if I co-deposit and I calculate how many palladium atoms I'm adding in thickness here, I can measure the excess heat here. And I was actually able to show that as we grow the co-dep layer, we get more excess heat out. We'll talk more about that later.
These are this is an optimal operating point manifold. If we look at excess power created by a cold fusion system, and we look at a function of the input power in watts, people say we only do milliwatts, but jeepers, here we got 6 to 8 watts input. This is in an aqueous system. What we find is, over time, as we generate more coat deposition, as we get more loading, we get more excess heat out. And these are optimal operating point manifolds. And so what we try to do is run the system right over here. And obviously, by the way, if you ran the system here, you wouldn't get any excess heat, or as much, would you? So how can we actually separate out people who claim they didn't see it, unless they do the whole region? We'll talk about where these come from. They come from the flow equation. Here we see the flow equation for deuterons. It turns out this is the second flow equation. This is the Navier-Stokes equation. This one for palladium. If we put them together, we generate different types of co-deposition. Spey-Wars uses this type. We use this type. We'll talk about the differences tomorrow. And classical cold fusions here, this is the classic Fleischmann-Pons effect. And the reason it's important is, if you don't generate excess energy until you hit a lattice ratio of deuterons or protons to palladium of 0.8, you're not going to get that till here. So these are going to turn on quick. And poor Fleischmann-Pons is sitting here waiting. This is a theoretical calculation, but that's why it took them 2 to 4 weeks to turn on. And with co-deposition, we can turn it on in under an hour. If you want to read about this on Brillouin zones, get Huizenga tonight. That's your homework assignment. It's a thin book. You can read it in one night, but you'll understand all of this stuff. It's really important. This is the palladium Brillouin zone. All right, 3RH. In our analysis of looking at where the excess heat comes from in palladium, we see there's multiple sites. These are pictures of palladium under different systems that have all generated excess energy. So here's Stringham's, Mitsubishi's, Spey-Wars. We do a lot of changes in the lattice. And these exophytic, looks like micro explosions bursts, are one of the reasons why I think the CAM theory is what's going on, where we have a sudden deloading, and I think the deloading is what's causing that, rather than anything else.
The loading or the deloading?
The deloading. I'm sorry, let me get a drink here. Any questions? Please.
Yeah, you mentioned that thin book, something. Could you tell us that again?
Huizenga. I think it's Introduction to Metallurgy.
You got it.
Introduction to the solid state. You'll be able to finish it in one night.
I had a question. You mentioned that unless the conditions are, proper, you won't see excess heat.
That's right.
Has anybody gone back and checked previous experiments to make sure that in fact was the case?
Do you think they'd want to know the reason why they failed? I mean, one of the things we're dealing with here is some people really who've already made their name by killing the field. Do they really want to go back and look? Maybe we should, though.
Yeah, I mean, that's,
I mean, maybe you have your next project.
Next assignment.
Yeah.
It'll be tomorrow.
Anyway, there's a lot of different regions here. I want you, when you think about palladium, I want you to think about the surface that we create with CoDep. I want you to think about the first 40 microns, and I want you to think about deeper. There seem to be multiple regions, and they may have a different role. And each of these regions may have a certain number of active sites, and we can do an integral and figure how many watts we can get out. Okay, so there may be microstates, and we talked about this before. There's another reason we think that we may be getting multiple states, multiple types of regions within the palladium, is when we look at the heat after death, as we talk about tomorrow, there appear to be different time constants. All right, I just wanted to run through some of this. You know all of that.
What's that picture that you just passed? I was curious.
Which? This?
The melted nickel or
just a piece of nickel. This is pretty. If you want to look at gold, I mean, these are gold atoms that somebody. It's amazing. Nobody in the last century could arrange atoms. And now we live in a time where you could make a heart and send someone a heart of gold. I mean, that is just so cool. Actually, gold is really interesting, and we use it in a lot of our systems rather than platinum, because I had this argument with Bockris back in '92, and I went to the meeting in Austin and said my gold anodes are dissolving and they're appearing on the cathode and giving me a slight excess energy of about 15%. And he yelled me down and said, gold does not corrode. And I had the pictures, and I'll show you. And you can see it depositing as a brown auric hydroxide on the surface. And we found that really important for reasons we'll talk about tomorrow. By the way, you know where the name platinum comes from, right? It comes from platina. It was found today when we dig gold out of the ground, we dig it out in troy ounces. But when Europe came to South America to take the gold from the Indians, it was removed by the ton. Now, one of the things that was a problem was the Indians had been using silver. And they also had actually found a way to use platinum for nose pieces and ear pieces. And the Europeans were unable to melt platinum until 100 years later. So to them, platinum was a waste. And so they named it platina, which you could tell me it's a diminutive form of silver. So what they tried to do was prevent people from using the platinum and making these fake coins. Spain spent a lot of time to make sure that platinum wouldn't go anywhere as part of their... all right, this is nice. This is $2 million worth of platinum. It's 1,000 cubic. We need platinum in our work, but we can't. All right.
Tabletops.
Any questions? Well, we're going to talk about electrical transconduction. That's looking at the DC response of a material. You put on an applied electric field, and you might want to, you look at the current, you might want to put on a big enough voltage that you pull all the charge carriers out. That's how we measure how many charge carriers are inside. Then what we do is we look in the AC. So we look maybe from 10 to the 9th hertz down to 10 to the minus 3 hertz. And I assure you, if you're going to balance a bridge down there, it's going to take a few days. Then we'll talk about some other things. So, transconduction. That just means we put on a DC current, we put on a DC potential, and we measure the current coming out. And you know all this stuff. What's interesting about water is most people in cold fusion in '89 were adding all kinds of salts. And I mean, the one who was really big at that was Stephen Jones, who added the kitchen sink. And so their electrical resistance is way down here. And what we use successfully, what works, is only this. I think this is another reason that people missed, and we'll talk more about that. Okay, let's see, we can skip all this. This is it turns out if you want to really build devices with dry cold fusion components and couple them to electrical, you've got to pay a lot of attention to resistance and thermal conductivity, which is beyond this. But if you go to the advanced course, we'll talk about it. Complex permittivity. We apply an electric field. This is the dielectric constant. It's actually complex. The real part is what we call the dielectric constant. The imaginary part, it turns out, is connected to electrical conduction, the resistance. And that makes sense because actually, if you have a material and apply an electric field, we get charge carriers. But if we have a polarizable material, all of the polarization will align along the electric field. And both play a role. Now, what's interesting, are there many kinds of polarization. We can have electronic, ionic, dipolar, space charge. There's a few others. What's interesting is they're coupled through Hilbert space. If you have a material that polarizes, that is a current, isn't it? So it turns out they're really tied together. And they play a role. So what we often do is we'll measure here from 10 to 3 to 10 to the, you never go up that high, 10 to the 9th hertz. And different relaxation spectra will begin adding in. If you're putting in an AC signal faster than the thing can respond, then its input no longer is added in. And that's why this starts coming down. As you increase the frequency, things can't keep up that are high mass. So you lose these first, you'll lose those second. Okay, so we put on an AC signal. This is me upstairs back in '67. We're growing ice over and building, was it building 28? What was the building that they tore down?
20.
20. That was at 20. That was in the time when there was a lot of room here. And okay, so what we're doing is we're measuring from here up to about here. Peter will be talking about other interesting effects over here. I don't want to get into the bispectra, but that's basically what you, all right, we got to do this. Basically, I told you, as we increase in frequency, some things cannot keep up with those changes. And so their contribution falls off. That's a Debye spectrum. And so we see this with all kinds of materials. Let's say picric acid. Here the proton jumps from one side to the other. And so what we see, there's a certain peak, and after that it begins to fall down. It no longer can contribute.
Is that a resonance peak or?
No, good question. Who said that?
Right here, the guy that's going.
No, it's not.
Right.
Relaxation is very different from resonance.
Okay.
And your second assignment is go get von Hippel's book. He wrote 3 great books, Dielectrics and Waves, Molecular Science, Molecular Engineering. And you can go through, it's important to see the difference between resonance and relaxation. Great question. This is where the relaxation spectra of water kicks in. Okay, we can skip all of this. What's interesting is when we look at water and freeze it to ice, the spectra of water, which is around 10 to the 10th, 10 to the 11th hertz, goes to lower frequency. And it comes down to about 10 to the 3 hertz, 10 to the 4th hertz. And we can resolve different structures in here. And the reason that's important is in the 60s and 70s, we figured out how water works. And here's how it works. It turns out that many people thought that what was going on is water has a dipole moment, and they thought all of the water molecules just align. But if you work it out, it creates an antiferroelectric system. It actually moves in the wrong direction. And what seems to happen instead is the protons jump. Initially, you have two protons on every oxygen molecule, but you have 4 sp3 orbitals. So if one of the protons jumps to an empty orbital, for example, here to here, now you have a double defect where there's 2 protons on here. This one will jump to here, this one will jump to here. Normally, this will be a sphere. But if you apply an electric field, it'll become a drift ellipsoid. Okay? So again, let's go through this. As a result of a microwave rotation and an anti-symmetric infrared vibration, we get a movement of proton or deuteron to one of the empty sp3 orbitals. That creates a double defect, and the next one will drift down. The result is that these defects will drift all the way over a very long distance, and that is the origin of the high dielectric constant of ice and water. Ice being about 100, water being about 80. And that gets us to any questions, and then we get to electrochemistry. Okay, take-home point is water, think of water as a solid, think of it as 2 lattices, and it's connected to 2 lattices in the palladium. So we got 4 lattices involved. Let's talk about electrochemistry. The most important rule in have you all studied electrochemistry? By the way, I've got one other question here. Is anybody, how many people here have done cold fusion experiments? Okay, not many. All right.
You want to.
Well, you will after this. It'll be easy. In electrochemistry, we rank things on an electromotive series, and the important rule in electrochemistry is probably the only thing you got to remember to take home. The anode is the site of corrosion. If you got that, you're pretty well okay. The cathode is protected. The anode dissolves. If it's iron, we call it rust. We don't call rust any other metal, but we can say it corrodes. Now, normally you need 2 electrodes. It turns out if you have just a piece of iron, like on a wet fence that the city puts in, you'll have an area where water will make it the cathode, and this portion will dissolve. The anode is the site of corrosion. So, you know, go to where your iron by your house. If you scratch it off, you'll see the orange hematite that's Fe2O3. You go underneath it, you'll see some antiferromagnetic ferrite that's Fe3O4. You go down a little farther, you'll see the white FeO. All of that stuff's just sitting there. All right, let's skip ahead. When we look now at the electromotive series, so let's take magnesium, very high electromotive active. We know that sodium, magnesium, put it in water, catch fire, very active. Nickel is noble with respect to iron, but it's active with respect to hydrogen. Now what happens is, when you connect materials up, they go from their theoretical voltage and they start coming down for two reasons. And so you're using two electrodes, and how they come together depends upon whether there's resistance control or not a control. But basically what's happening here is we go from the theoretical down to here, and what Peter will teach you tomorrow is we have an activation region, we have a concentration polarization, a Tafel region. So he's going to talk about the rate limiting effects of each of these. I tend to not use the Nernst equation because this is only good at equilibrium. And I think everything we do in cold fusion is non-equilibrium. We keep driving these to non-equilibrium regions. So what we have done instead of using the Nernst equation is to use these Navier-Stokes equations, as I'll go into tomorrow. Let's skip all this. The only reason this is important now is when we look at ionizing radiation interactions, there's three regions. There's the photoelectric region where lead will protect. Lead isn't going to protect you here because the absorption isn't even a function of Z here. Here it's a function of Z. Anyway, there's one other issue. Anyway, we can skip all. It has to do with build-up. Any questions? Okay. I'm going to let it go for today. We'll start talking about aqueous systems and calibration tomorrow. Okay?